Today I want to talk about a better way to estimate the area under the curve. You know, last time we did the estimating the area under the curve using rectangles. How do you improve the accuracy of the estimate? The easy way, or at least from a theoretical standpoint, the easiest way to improve the accuracy is just increase the n, that is draw more rectangles. But actually, there's another way that you can do it, and that is by changing the shape of the thing which you're drawing. Rather than draw rectangles, draw some kind of other shape. Here's the basic idea. Let's look at this one, and let's imagine I did, say, rectangles on the left endpoints. It would look something like this, right? This would be 4 rectangles on the left endpoints. And you can see this is, a little bit accurate, but this area up here is getting missed by the rectangles. Here also, and then over here we got some extra area. All right, the idea, what I just said, let's draw the rectangles, or not the rectangles, let's draw some kind of other shape which will fit the picture nicer. Here's the idea. I'm going to draw this shape. Hope you can see this blue happening. Ooh, like that. All right, can you see that? This is like a rectangle, but on the top it has a triangle. Instead of just going straight across, you go across like that from point to point on the top, right? Like so. This still is not going to give you the actual area, because the pink line that was on there before is actually slightly curved, so it's not going to be the same as this straight line, but it's much, much closer, isn't it? I mean, you can't even see the difference on my picture. Here's one there, all right? You can see a little bit of area is being left out there, and also a little bit of area is being missed, or being missed over here. Okay. Anyway, what kind of a shape are these? The blue shapes. These are it's sort of rectangular, but it has that thing. Actually, if you turn your head sideways, you'll see these are trapezoids, aren't they? You know, usually we draw a trapezoid this way, something like that. That's a trapezoid. It has 2 parallel sides and 2 sides which are not parallel. That's a trapezoid. It's sideways when you draw them like that. All right, these are trapezoids. The method for doing the area under the curve in this style is called the Trapezoid Rule. And I'm not sure why the word rule is used. It doesn't really seem appropriate to me, but anyway, who am I to change standard terminology. These are trapezoids. So estimating the area using trapezoids, you can tell just from the picture here, you should expect this to give you much better approximations to the area. Unfortunately, the formula is going to be more complicated. It turns out, though, actually, the formula is more complicated, but it's only very slightly more complicated. So if it's up to you, if you're doing this in the real world, you should basically always do the trapezoids rather than the rectangles, because the formula is only very slightly more complicated, but it gets you a much better estimation of the area. All right, let's talk about the formula. Actually, let's talk about it right now. I want to say another thing about this picture. What if I'm going to additionally draw on this picture the left hand? So originally I drew the left hand rectangles. Those are the pink ones. I'm going to draw the right hand rectangles also in orange. All right, they go up here. Okay. This one actually is further down, the right hand. All right. Anyway, those are the right hand rectangles. I would like to know, and this is an easy thing once you see it, geometrically speaking, can you say what the area of the trapezoid is? That is the blue shape, in relation to the area of the 2 rectangles, the pink rectangle and the orange rectangle. There is a relationship between the areas. You know, there's some formula you probably learned at some point for the area of a trapezoid. I don't really want to get into that, because you can see pretty clearly what's going on here. The area, let me just write, this is an obvious fact once you see it. The area of the trapezoid is the average of the 2 rectangles. Right? It really is, because, I mean, look at this one. The pink one is down here. The orange rectangle is all the way up there. And the blue rectangle cuts the difference in half. Not the rectangle, the trapezoid. It cuts the difference in half, right? You get all of this area, which is common to both of the original rectangles, and then you just cut the difference in half. So it has to be the average, okay? So the area of the trapezoid is the average of the two rectangles. That means the formula for the trapezoid approximation, you just average the left-hand side a rectangle approximation and the right-hand side rectangle approximation. And that's pretty easy to do. Let's write it as a formula. Okay, in the situation when we are trying to estimate using rectangles, you draw the little chart of the values. It's a simple chart just from the lower value to the upper value. If I call them, just for the purposes of writing this next formula, if I call them x0 and then x1, x2, etc., the last one xn, the previous next to the last one xn minus 1, the rectangle sum, so the left rectangles would be, remember how you do this, you do a big sum every time you multiply delta x times each one of these. When you're doing the left though, you start with this one. So the left rectangle sum is delta x times f of x 0 plus delta x f of x1 plus blah, blah, blah. And you go across and you stop there. Delta x f of x n minus 1. Right? This is the left hand side, and remember delta x is b minus a over n. All right? And the right hand side is almost exactly the same. The difference would be you start at x1 and you end at xn. So it's delta x f of x1 plus delta x, come on now, delta x f of x2, blah, 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 delta x f of x n, like that, right? This is the right hand sum. What I said was the trapezoid approximation is the average of these two. So to get the average, you add them together, and you can see actually most of the terms in here are repeated in each one. Not quite all of them, but most of them are. You add them together and then you divide by 2. So the trapezoid estimate, here's what we're going to use. I'm going to rewrite this formula, so this is not quite the final version. But you just add these together. What you get is this guy, delta x f of x0, plus you get this one, x1, but you also get it again here. So when we add them, you can think of it as like vertically adding these together. You get 2 delta x f of x1 plus 2 delta x f of x2. All of them have a 2 in front of them except for the last one here, which only has a 1. So I'm going to say the second to last one, 2 delta x f of x n minus 1. And then the very last one does not have the 2. Delta x f of x n. All right, sorry I'm way down in the corner there. I'm going to simplify this just a little bit by factoring out the delta x, right? Everything here has a delta x on it, so we can factor the delta x. Oh, you know what? I forgot. I added them, but I didn't divide by 2. That's what you do when you take the average. So put a little 1/2 in front of this whole thing. All right. You add it all up, and then you multiply the whole thing by 1/2. Okay. I'm going to rewrite this, but I'm going to factor the delta x out, and also I'm going to distribute the 1/2. It's going to cancel all these 2's, except on the first one and the last one, which didn't have any 2's. Here's what you get. All right, this is the formula for the trapezoid rule. What I did, I just did this thing. What I said I was going to do is factor out the delta x, which I wrote b minus a over n. That's what delta x is. And then multiply in the 1/2. Why? It shouldn't be a 2 there. Sorry. I left the 1/2 outside, but I said I was going to multiply it in there. All right? b minus a over n in the front. And then I distributed the 1/2 everywhere. That has the effect of canceling out all these 2's. And there are 2 terms which didn't have the 2, so they get 1/2 on them. So that's the first one and the last one. All right. This is the formula for the trapezoidal rule, and you should memorize this. I hope you believe me when I said before, this is slightly more complicated than the rectangle thing, because you got to remember this 1/2 and that 1/2. But it's not a big deal, right? And it gives you a much more accurate estimate. So in the real world, you should basically never use the rectangles strategy. If you want a more accurate result, you should always use the trapezoid rule because it's more accurate. All right, that's the trapezoid rule. Let's do an example of this. Here's my example. Let's estimate the area under the curve from 1 to 4 of the square root x dx using the trapezoid rule, with n equals 6, okay? When you do the trapezoid rule, you don't say the left points or the right points or whatever, because it's not like that, see? N equals 6. So anyway, we should begin by making our little chart as usual and decide what are the values that I'm going to be plugging in. This time I'm going 1 to 4. Can you divide that into 6 pieces? I think you can. If I go 2, 3, that's 3 bits, and then 1.5, 2, 2.5, 3, 3.5. This is 6 intervals, all right? So that's my points for n equals 6. I think we're ready, I guess, to just basically write the answer, right? Because this is going to be x0, this is x1, x2, x3. So what is the answer? The area under the curve is approximately, according to this formula, b minus a over n here is going to be, well, b and a are 4. I'll write it all out. 4 minus 1 over 6, right? And then inside I say 1/2 f of 1 plus f of 1.5 is the next point, all right, etc. The last point without the 1/2 on it is a 3.5. And then 1/2 f of 4. This is basically, well, this is the answer, although you should, just so that I know that you know what you're talking about, you should plug in for the f's here. So your final answer, I guess you could simplify, that's 3 over 6, which is 1/2, right? 1/2 square root 1 plus square root 1.5 plus blah, 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 blah. Every time you see f, that means the square root. So here, square root 3.5. Finally, 1/2 square root of 4. That's that. This is the value for the trapezoid rule. If you want, you could plug this into your calculator. I did plug this into my calculator. I got 4.6615. All right, and just for your information, the actual value of this actual area under the curve is 4.6 repeating. So this is actually quite close to the real deal in this problem. All right, quite accurate. In fact, you can make this a little bit more accurate with a slightly different shape, all right? This one, the shape is quite a bit weirder than trapezoids. It turns out the formula is, again, slightly more complicated, but not very much more complicated. Let's do it. In my opinion, the trapezoid rule is not all that crazy. You know, it's a fairly natural thing. I think it's something that anybody could come up with themselves. Instead of drawing the rectangle there, you draw something which has that extra little triangle on the top. It's not a huge, you know, cognitive leap to come up with that on your own. Simpsons rule, I think, is a considerably less obvious idea. Here's the idea, though. Instead of, just like in the trapezoid rule, you kind of break it up into these bits here, all right? The shape is going to be different, though. You go up to the curve on the 2 endpoints of each interval. So you go up to all these points. Now, if you're doing the trapezoid rule, you would just connect these with a straight line and you get the trapezoid. The idea with this one is you do not connect these with a straight line. You connect them with a parabola, all right? There is a parabola that goes through these points. Now, the way that you do a parabola, you know, any 2 points determine a specific straight line between them. This is not true of a parabola. If you have 2 points, there are many parabolas which go between them. So in Simpsons rule, you use kind of 2 adjacent blocks of subintervals, and you draw the parabola. So for instance, over here, with these 3 points, the parabola, there is actually a unique parabola which goes through these 3 points, and it would look something like that. I don't know. This is not a great rendering of a parabola, but it would look something like that. And the idea is you use this kind of a shape which is rectangular, but it has a piece of a parabola on the top. All right? And over here also, there is some parabola. This one's kind of hard to see but because of my picture. Maybe it goes this way. Oh, that was pretty terrible drawing. You know, the parabola might go up or it might go down depending on how the points are arranged in your picture. But anyway, the shapes. So in Simpsons rule, uses parabola capped rectangles. That says rectangles, all right? I hope you agree with me. This is not really an obvious idea, although I hope it makes sense. You know, you draw this sort of rectangle thing, and then you put a parabola on top of it rather than putting a straight line, which is a trapezoid, all right? This is called Simpsons Rule, and there's a formula for Simpsons Rule. It turns out, in my opinion, the sort of shocking thing is that even though this is a much more complicated idea, the formula actually doesn't look very complicated at all. It's a slight variation on the formula. So I'm not going to give the derivation of this because it's quite complicated, but the formula is really easy to use. So I'm just going to tell you what the formula looks like, and we'll do an example. All right, here's the formula for Simpson's Rule. The area under the curve is approximately b minus a over 3n. Okay, here's one difference from the trapezoid rule. In the trapezoid rule, we had b minus a over n in the front. In Simpson's Rule, it's b minus a over 3n. On the inside, we are going to have some coefficients on these. Again, it's going to be added, all the points added together. Some will have coefficients on them, and here's how the coefficients go. It's f of x0 plus 4f of x1 plus 2f of x2 plus, and in here the coefficients alternate, 4, then 2, then 4, then 2, then 4, then 2. All right. The second to last one would be a 4. The way that this always is going to work out is the second to last one is a 4 in the front. n minus 1 plus the last term f of xn with no coefficient. All right. So in here you alternate coefficients. You alternate 4, 2, 4, 2, etc. All right. That's how we do it. Okay, this is the formula for Simpson's Rule. If you think about it, this alternation, in order to end up with a 4 here, this whole scheme will only work when the n is even. That's actually because, if you recall from the picture, the Simpsons Rule uses 2 adjacent blocks to build the parabola, so the number of blocks has to be even. So n must be even. That's not a real restriction. If you ever, in the real world, if you found yourself needing to do this with n equals, 99, you should just forget about one of them. Use n equals 98 instead, and then do Simpson's Rule. And it would be, usually when you decrease the n, you lose some accuracy, but since you're using Simpson's Rule, it's going to be super accurate anyway. Okay, this is the formula. Again, you'll have to memorize this. I hope this is not too difficult to memorize. It's very easy to use. Let's just do an example. I just want to do the same example we just did. The integral from 1 to 4 of root x dx. Remember, the trapezoid rule said the answer was 4.66 something. The true answer is 4.6 repeating. So we matched to the 3 digits on the trapezoid rule. Let's see how good the Simpsons estimation is. Let's just do it, right? Let's make our little interval here, right? It's exactly the same from the previous problem, 1 to 4. Whether you're using trapezoid or Simpson, you're going to use the same points either way. 1.5, 2, 2.5, 3, 3.5, 4. Okay, and we just plug into that formula. Let's do it. We can do it right here, can't we? b minus a over 3n. So that would be 4 minus 1 over 3 times 6, right? n is 6. I should have written the problem. I'm doing the Simpsons approximation for this area under the curve using n equals 6. What goes on the inside? This stuff. So f of x0, that's the 1. So this is f of 1 plus 4f of 1.5 plus 2f of 2 plus etc. Alternating 4s and 2s. The second to last one will have a 4 plus 4f of 3.5 plus f of 4. That's that. All right. Again, when you write your final answer on a test or something, I want to know that you know what you're talking about when you say f. So you should write one more step, which has the actual function in there. All right, my final answer. I simplified the front there a little bit. 4 minus 1 is 3. 3 over 3 times 6, you can cancel 3. So you get 1 over 6. And then 4 times square root 1.5 plus 2 root 2 plus 4. I'm going to write it all out this time. Plus 2 square root 3 plus 4 square root 3.5 plus square root 4. There you go. if you want to do, if you want to see the number for this, you can plug all of that into a calculator. Here's what you get. The answer is 0.4, no, 4 point, come on now, 4.66656, blah, blah, blah. All right, etc. Very accurate. Remember the true answer is 4.6 repeating. 6 is all the way. So this is matching up to 4 decimal points, which is pretty impressive using only n equals 6. Only 6 data points, but it's still extremely accurate. So Simpsons rule, again, like I said before, the Simpsons rule formula is still fairly easy to do. So in the real world, if you're actually trying to compute definite integrals, you should basically never use rectangles. They're very inaccurate. And also there's no real good reason to use trapezoids. You always might as well use Simpsons rule because the formula is not considerably harder to do and you get a more accurate answer. So Simpsons rule is actually very commonly used. There are better approximations, better than Simpsons rule, but people generally don't go that far. Usually Simpsons rule is good enough for most uses in the real world. All right, I think that'll do it.